over time, but here's a simple one. It's constant for a while, and then it drops to 0. Yes? I meant 20, thank you. So that's probably worth a point, and I'm getting confused, though. I'm saying? Brianna, that's right. You got that, Jeff? Thanks. Yeah, great. Yeah, thank you. Okay, so that's a simple sort of pattern for yt. So we can plug that into the general formula. You know, you guys could compute that on your calculators if you punch buttons 20 times, or if you write a couple lines of code, you could do it much more quickly than that. There's also a general formula we can come up with for this case that's kind of useful, though. So what we really want to know in this case is the present value of this investment, where we have y times the sum t equal 1 to cap t of 1 over 1 plus r raised to the t, but where t is less than infinity, t would be equal to 20 in this case. Yes? Yeah, so the timing convention I'm going to use here is make the investment at time 0. You start realizing benefits at time 1 through time 20. Oh, I see. Yeah, that's fine. That's fine. I suppose that's worth a point too. Okay. Okay, good. All right. So this is the arrangement we want for our payoffs. It'd be nice if we had a general. Again, you just add. T is equal to 20. You could just add this thing up 20 times and get the answer. There's nothing wrong with that, except it's a little bit tedious. It'd be nice to have a general formula for this. In this case, we can get one in a kind of nice way. That's pretty simple. And the way we do it actually is by using the same formula we have for a perpetuity. So here's how I want to do it. So in this case, where we have a finite value, a finite lifetime for this asset. You can think of this as it's kind of like an annuity, by the way. So does anyone know the difference between an annuity and a perpetuity? The way they're treated in insurance, at least. What's that? Okay, well, so they both typically pay off once a year, actually. Yeah. Yeah. So the perpetuity is like, as the name suggests, lasts forever, or until until financial firms cease to exist. So it lasts forever. An annuity is usually designed to last a finite amount of time. They're often designed to last for as long as the beneficiary is alive. So if you assume you know how long you're going to live, at least it has a finite lifetime. So let's think about the case where we know cap t and think about this as being like an annuity. What I'd like to observe is that the value of this thing is equal. Let me write it this way. So let's do this. So the sum of 1 over 1 plus r to the t, into this t equals 0 to plus infinity, is equal. Cap t is equal to the sum t equals 0 to cap infinity of 1 over 1 plus r raised to the t. So this is the value. This is related to the value of a perpetuity minus the value of a perpetuity if you only receive the perpetuity t years from now. And so if you receive it t years from now, the value of that is 1 over 1 plus r, all raised to the cap t. So you see the setup here? So this is the value of an annuity, or perpetuity. But now imagine that we take away the perpetuity from you after 20 years, or after t years. Okay, so the value of t years out is this, but you're going to discount that cost by 1 over 1 plus r raised to the cap t, because it's happening t years in the future. Is that clear? Maybe not. So anytime we get a payoff, remember if we get a payoff at date t, or the present value of this has value of y cap t times 1 over 1 plus r raised to the cap t. Because if you invested v today and held that investment for t years at an interest rate of r, you get back a return of 1 plus r raised to the t. So if you receive a payoff in 10 years of $1, say, the present value of that is 1 over 1 plus r raised to 10 years in that case. So what I'm doing here is taking a perpetuity that I get today and subtracting the value of a perpetuity that I get 20 years from now. And the difference between those two things must be the value of the payments that I get between now and 20 years from now. All right. So we can use the trick for these infinite sums now. So we'll write this infinite sum we know is just equal to 1 plus r over r. We worked out the value of this perpetuity before. This will be minus 1 over 1 plus r to the cap t times the same thing, 1 plus r all over r. And so then we're going to be able to simplify some stuff here. So this will be equal to, let's go ahead and factor out 1 over r times 1 plus r minus 1 over 1 plus r to the t, but then minus one of these. And so we've got now 1 over, I can factor out a 1 plus r, and what I wind up with is 1 over r, 1 plus r minus 1 over 1 plus r to the t minus 1. So that gives us an expression for the value of this sum from t equals 0 to cap t. And if we have t, sometimes we'll have t equal 1 to cap t, in which case you need to divide through by 1 plus r. All right. Okay, so with those, any questions about that sort of calculation before we move along? Yes. You mean from this step to this step? Oh, yeah, I mentioned that. Let's see. So I should have a 1 plus r here, minus 1 over 1 plus r, and then I should have so I think that's the one I meant to pull out. So I think I pulled out this. Oh, I see. So you think I should have a t here? No? Oh dear. Let's see. Okay, I'm going to do this. Katie, I would like you to get an extra credit point for pointing out the problem, and then I will give 2 points to the first person to email me a nicely written out correct solution to this bit of algebra, because I'm terrible at doing this in front of you guys. Okay, so look for a correction. Let me put a little question mark here. Let's say check. Okay. All right. So other questions before we? So let me partly excuse myself. This is more or less right. There's a factor 1 plus r here around here that's mysterious and depends on details of the timing. So go ahead and get it right, but this is approximately correct. Yes. Good. Okay. So same deal. So somebody can send me confirm an email with the math worked out. That'd be great. I'll let Katie keep her extra credit point though. I want to not get bogged down in my possible algebra mistakes because we're already late today and I have exciting things I want to share with you this lecture. Yes. Yeah, so there's this kind of annoying bookkeeping, right? But there's a distinction in timing here, which is important because it adds a factor of 1 plus r or 1 over 1 plus r. If we say that if this sum here, t equal 1 to cap t, suggests that payments start next period, so not in the initial investment period. If we said t equal to 0, then that would be the appropriate thing to use if we got payments or that began the same period. So in the solar cell example, if we made the investment right now and the same year we made the investment, we realized savings of $450, then the appropriate timing convention would be to say t equals 0. But if we make the investment now in November and not realize savings until next year, then the t equal 1 convention may make more sense. Okay, either it doesn't, this is a bookkeeping detail, and it's you should try to get it right, but it's not sort of critical because the magnitudes of r that we typically see are like 1%, 5%, 10%, and dividing by a small number like that is much more important than multiplying by a number like 1 plus that. So in terms of the magnitude of the numbers you get out of these calculations, the 1 plus r term typically doesn't matter that much. Okay. All right. So let's move along. So I want to talk now about extracting resources over time. So we spent some time last week thinking about a static resource extraction problem. So the story I was telling was one involving oil firms who had a stock of oil. They could extract that oil and sell it, and the size of the stock affected the marginal cost of extraction. But the world only lasted for one day, so there was no dynamics, there was no intertemporal decision facing these firms. Now, in a more realistic model, that's not a very realistic assumption. And now we have the tools to think about the problem facing a firm that's trying to extract oil or some of the natural resource and doing that over time. So here's how I want to proceed. I want to think about the firm having a cost function. So the setup is going to be very similar to what we had before. There will be a firm that's trying to maximize its profits, but instead of maximizing profits in one period, the way we did before, what it's going to try to do is maximize the present value of its profits over time. So before we had profits for the firm that were equal to the maximized value of y minus c y s, and prices mattered as well, of course. So we had the cost function depending on the stock that was in there before, but we just earned profits for one period. So now what we're going to do is going to be a little bit fancier. We're going to instead try to maximize profits. So we'll put a t on here. So this is profits in time t, and that quantity will be equal to the amount extracted in time t. Sorry, I need to put a t on here as well. So let's make it prices at time t, output at time t, costs given stock at time t, and output at time t. So this is the profits realized in time t, but then what the firm's going to maximize is going to be the present value of this. So we'll call that thing t equal, actually, what am I calling that? Yeah, I'm going to do this from t equals 0 to cap t. It's going to be the present value, so we'll have 1 over 1 plus r, all raised to t, and then we'll have this expression for profits here. So pi t or pt yt minus the cost function. This can depend on t also. So that's going to be the new setup. Now there's one important thing I need to add here. It's that the stock depends on how much I extract. That's sort of the key innovation. So at st, we'll have a stock which is equal to the stock we had last period minus whatever was extracted last period. So the way to think about this is, the firm starts off with a billion barrels of oil in the ground, and if it decides to extract 100 million barrels today, then tomorrow it has 900 million barrels left. Yeah. So let's assume that 1 unit of Y is. Yeah, these are all measured in the same units. This is like barrels of oil. Yeah. So in like the graphic we have Yeah, so the petroleum business is an interesting one. If you get a barrel of oil, you take that thing and you turn it into a bunch of different products, and you have some control over what products get produced, and I'm ignoring all of that. Yeah. If you wanted to pursue that, what you do is you think about YT being, like a vector of different outputs. Like here's your kerosene, here's your heavy oil, here's your gasoline, and it'd be a vector of prices as well. And you probably just under the cost function too to deal with refining costs or whatever. If you want to avoid that, you can also think of this not as being a firm that operates refineries, but just a firm that operates an oil field and sells the petroleum they extract to a refiner. That's probably the easiest interpretation of this. Okay, other questions about the setup here? All right, so the firm's problem can be written this way. This is all subject to this constraint, which is going to have to hold in every single period. We can, this is an equality constraint. What I actually want to do is substitute this into the objective function. I can do that. So this is all the same as maximizing the sum t equals 0 to cap t, 1 over 1 plus r to the t of pt yt minus ct yt. And then I'm just going to substitute in for st. So I'll have st minus 1 minus yt minus 1. Okay, so that's the firm's unconstrained problem. I need to tell you the choice variables. This is going to be a sequence of yt's. So this is for t equal to 0 to cap t. And there's another constraint here, which you should keep in mind. This is going to be given some initial stock of s minus 1, which is the amount of oil you have in the ground, or the stock of the resource you have in the ground before you ever start extracting. Okay, is that clear? So every period, this is equal to pi t, the profits the firm earns in time t. And the prices can change over time. The cost function can change over time. Why might the cost function change? Remember that we're already taking care of how stocks might affect things. Well, the price of goods could change over time. So we haven't included the prices of inputs here explicitly. So that's prices of labor and capital could change, for example. Technology could change. If we have technological improvements, if we have, like we were using a production function that looked like something like this if we had t's on it. Sorry. We used a production function that looked like this before. So if, and we interpret this DIT as being something related to technology, if there are technological improvements in our ability to extract oil, that'll affect the cost function because this DIT shows up in the cost function. Okay, good. So that's the nature of the problem. Let's go ahead and take some first order conditions here and see what we get. So the firm's going to choose YT in every period. Let's just go through and see where so fix a particular YT. So like think about Y, t equal to 3, for example. So where does Y3 show up in this thing? Where's the first place that Y3 shows up? Yeah, here. This is so revenues in period 3, where t is equal to 3. That's the first place it shows up. And so we'll get the first order condition for this thing will involve PT, just taking the derivative of that. Where else does it show up? Well, it shows up here. So we'll have minus the partial derivative of the cost function at time t with respect to extracting YT. Okay, so that's good. Where else does it show up? Just reading along. Well, there's YT minus 1 here. So where else does Y3 show up? Let's imagine writing this out. I just want to write out this sum. So I didn't push that up far enough. Okay, so anyway, the sum I've got is 1 over 1 plus r to the t equals 0 to cap t of pt yt minus ct yt st minus 1 minus yt minus 1. Okay, so I just want to observe that that's equal. Let's take t equal to 0. Well, so that's 1. So it'll be times p0 y0 minus c0 y0 s minus 1, which remember is the initial stock we start with, minus y minus 1, which I think we can take equal to 0 actually. So that's all fine. Plus 1 over 1 plus r. We're taking t equal to 1 now. So this line is t equal to 0. This line is t equal to 1. 1 plus r times p1 y1 minus c1 y1 times s0 minus y0. So that was the decision we made here. And then 2 equal to 2. We have plus, help me out here, what do we have? 1 plus r squared times what? P2 y2 minus, thank you. And then here. Yes, very good. Okay, now we got t equal to 3. So this is going to give us plus 1 over 1 plus r to the cubed. P3 y3 minus c3 y3 s. Okay, we're almost there. T equal 4 gives us plus 1 over 1 plus r to the 4th. P4 y4 minus c4 y3. I'm sorry, y4. Then what? Minus y3 plus dot dot dot. I'm on board, so I better stop. Does y3 appear? Are we done with y3? Does it appear in any future terms? No, it doesn't at all. Just like y1 appears here when we actually extract it, and it appears in the costs we have next period, and that's the only time it appears. So y3, to take our earlier example, shows up in period t's cost function here, or period 3's cost function. It also shows up in period 4's cost function here, and that's it. The only place it shows up is here. So back to our general case. When we take the derivative of this with respect to pt, what term do I still need to have here? Yeah, actually it'll be, so I'll get a minus here, but times plus the next thing, so let's say plus dc what? T plus 1. It affects my extraction today, it affects my marginal costs tomorrow. dst, this is with respect to the stock, and this whole thing had better be, and there's one other thing we're missing. What is it? Can you see it up there? Actually, we're missing it for all this stuff. I'm not being sufficiently careful. There's a 1 over 1 plus r to the t that multiplies this stuff. And there's a 1 over 1 plus r to the what that multiplies this stuff? The t plus 1. And at the optimum, this has to be equal to 0. Yeah? We haven't said what this